Hello there! In this video we're going to be going through an example problem of what's typically referred to as a half-Atwood machine. An Atwood machine is a system that's got a pulley and two blocks on either end. This one's a half-Atwood machine because only one block is hanging over the end. So let's read the problem and then get started. A 5.00 kilogram block is on a table and is pulled to the right by a rope. The rope is strung over a pulley and a 3.00 kilogram block is hanging over the edge of the table. The friction force between the 5.00 kilogram block and the table is 15.0 newtons. Our goals are to A, determine the system's acceleration, B, determine the magnitude of the tension in the rope, and C, determine the amount of time it takes for the hanging block to fall 1.25 meters, assuming it starts from rest. So we're going to start here with part A, finding the system's acceleration. As always, when solving problems, the first thing we're going to do is draw a picture. So here is the situation. I've labeled our two blocks with a mass M1 and a mass M2, and then there's the string over the pulley connecting them. Next, we want to define our system. Here we're finding the acceleration of the whole system, so we're going to choose both blocks and the rope that's attaching them. Even if I were just trying to find the acceleration of one of the blocks individually, this is probably the system I would choose still, because the system acceleration will be the same as block 1 acceleration, which will be the same as block 2 acceleration. They are all connected. And this system allows us to ignore the tension in the rope because that's internal to our system, as we will see later in this video. So next thing I'm going to do is draw some force diagrams. I've drawn the force diagram for the blocks on the left. There's a tension force pulling it to the right and a backwards friction force resisting that slide. There's an upward normal force on block 1 by the table and a downward gravitational force on block 1 by the earth. And my subscript definitions are all there. We're using type of force, feeler, then dealer notation with those three subscripts. Next, I'm going to draw a force diagram for block 2. There's a gravitational force on block 2 by the earth, pulling it down. There's an upward tension force on block 2 by the rope, pulling it up. We know that the downward gravitational force is greater than the upward tension force in magnitude because that block is accelerating down as it falls. We also know that this is a continuous rope. We've got an idealized rope here, an idealized pulley, and so the tension distributes itself evenly throughout the rope, meaning that the tension pulling forward on block 1 is equal in strength to the tension pulling up on block 2. Next thing we're going to do is define our sign conventions. Remember that pulleys redirect motion or redirect force. That's one way to think about what a pulley does. And so we're going to use this generalized sort of curved axis along which we're going to do our analysis. So the axis starts going to the right here from block 1, but then it curves down here along the pulley and then starts pointing in our downward direction after the pulley has redirected that motion. So what that means is over here for block 1, the positive x direction is to the right, but as the pulley redirects that motion, the positive x direction for block 2 is pointing in the downward direction. So let's keep going from there. We've got our givens. We're always going to write down our givens. We know the mass of each block. M1 is 5 kilograms. M2 is 3 kilograms, both to 3 significant figures. And the strength of the tension force on block 1 by the table is 15.0 newtons, and it points to the left as drawn in our picture. Our find here for part A is the acceleration of our system in that curved x direction. So we're going to solve a force problem. We're always going to write equations both based on the motion and the force diagrams we've drawn. We'll break it down as vector equations, then scalar equations. We'll simplify things down and then combine. So this system is accelerating. So our equation based on the motion here is that the net force in the x direction is equal to the mass of our system times the acceleration in the x direction. And when you're doing Newton's second law, that m there is always the system mass, whatever system you've chosen. Here that'll be 8 kilograms, m1 plus m2. Now we're going to look at our force diagram and write an equation based on the motion. Here we have two objects in our system, so we actually need to look at both force diagrams. I'm going to start by looking at the force diagram for block 1. And when I add up the force in the x direction just for block 1, we have this tension force pulling to the right and this friction force back to the left. And for block 1, the left-right direction is our positive x direction. But I'm not done yet because it's not the only object in my system. I'm going to keep following along and look now at block 2. For block 2, the x direction is up and down, and so we need to add in the gravitational force on block 2 and the tension force on block 2. However, you may notice that the tension force from block 1 is in our positive x direction. The tension force from block 2 is up, which is our negative x direction, and they have the same strength. So when we add those two tension forces together, they'll add to 0. And so we don't actually need to worry about the tensions, which was the benefit of choosing this system to begin with, as I mentioned earlier. The rope is internal to our system. This is not an external force. And so we don't really need to worry about the tension when adding up our forces in the x direction when we are looking at the two-block system. And so really, you don't even need to write this first line. I just did that for emphasis. All you really need to write is that we have the gravitational force from block 2 pulling things in our positive x direction. Then we have the friction force on block 1 going against our positive x direction. All right, we're now going to write this as a scalar equation. When we do so, I see 1, 2, 3 vectors to worry about. And so let's fill in those parentheses. Our acceleration will be in our positive x direction. I actually didn't draw that into my picture. I should have, but I was already getting cluttered over there. Block 2 is both falling and getting faster as it falls, so that means the acceleration is downward. The friction force is backwards to the left, which is the negative x direction, and the gravitational force on block 2 is downwards, which is our positive x direction. So we've got a negative friction force and a positive gravitational force. We'll clean that up a little bit, make the left side just mass times acceleration in the x direction, make the force diagram equation. I'll move this gravitational force over since it's positive, and I'll do minus the friction force. And since these are both the net force, we can combine them and say system mass times acceleration in the x direction is equal to the gravitational force on block 2 by the Earth minus the friction force on block 1 by the Earth. A way to think about that is our net force, right? We've got the block 2 gravity pulling everything along the direction of motion, but then the friction opposes that. In this part of the problem, we are looking for the system's acceleration. So we'll go ahead and say, rearrange this equation for A by dividing both sides by m. And now this is looking pretty good. The thing I'm trying to find is by itself on one side of the equal sign. And let's look on the other side of the equal sign. Are all of these things in the givens list I made earlier? Well, it looks like only the friction force is. So I've got a little bit of cleaning up to do before I can plug in numbers. I'm going to focus first on this gravitational force, and I see that the subscript there is 2. So this is not the mass of the system. It's just the gravitational force exerted on block 2. And so I can rewrite this as not m1 or m, but m2g for that gravitational force. Because it's only the gravity on block 2 that's pulling things along the x direction as drawn. M is not in our variable list either, so I'm actually going to replace that m, which is, again, the system mass. It came from our original net force as mass times acceleration. And so I'm going to plug in numbers. It'll look something like this. Mass 2 is 3 kilograms. The Earth's gravitational field strength is 9.81 newtons per kilogram. I didn't explicitly write that in my givens, but that is always a given. And then we've got 15 newtons of friction force in magnitude. And then the M1 plus M2 is 5 kilograms plus 3 kilograms to 3 significant figures. When we plug that into our calculator, we end up with an acceleration whose value is 1.80 meters per second squared. And then we found the scalar magnitude of our acceleration, but if we're trying to find the vector quantity acceleration, we need to put a vector arrow back above the A and indicate that the acceleration has a magnitude of 1.80 meters per second squared, and it is in our positive x direction. And there we go. We're going to put a nice box around that. I've even kind of highlighted it with this yellow color to emphasize, there's my final answer, Mr. Miliano. Look here, we did it. So there we go. That's how you do part A of this problem, how you find the acceleration of the system. Let's go ahead now and move on to part B, where we are going to look for the tension in the rope. Now it would be a bad idea to choose the system that consists of both blocks and the rope connecting them, because we can't find the tension if the tension is internal to our system. And so instead we should choose a system that just consists of one block, and then the rope will be outside of that system. You could choose either block. I'm going to choose the block on the table. Now if we go look at that system boundary we drew, the rope leaves the system, and so it's now an external force. We're going to write our givens list. Anytime that you have found something in a previous part of the problem, it becomes a given for the later parts of the problem. So I have the same three givens as before, but from part A, we can add in that we have this given that the acceleration in the x direction is 1.80 meters per second squared in our positive x direction. And the find here for this particular problem is the tension in the rope, which we could write it as the magnitude specifically. The magnitude of the tension in the rope could be thought of as the tension on block 1 by the rope or the tension in block 2 by the rope. They have the same magnitude. I've left the vector arrows off of those F's because the force vectors aren't equivalent. They point in different directions, but they do have the same strength. This is a force problem again. I'm looking to find a tension, so I'm going to set up a nice table to help me organize my thinking there. The system here, which is just block 1, is accelerating. So we have net force in the x direction is mass times acceleration. Again, this is system mass, but my system has changed. It's just block 1. And so when I go to plug in numbers later, I'm not doing 8 kilograms anymore. I'm just doing the 5 kilograms of block 1. I look at the force diagram now, and I can say I have these two forces in the x direction, the tension force on block 1 by the rope and the friction force on block 1 by the table. And so we can make these scalar equations. Again, I have three vectors to worry about. My acceleration is in the positive direction. The friction force is in the negative x direction to the left for block 1. And the tension force is in the positive x direction, which is to the right for block 1. Simplifying this down, I can write mass times positive acceleration is just mass times acceleration. And then I can rewrite the force diagram equation as the tension force minus the friction force. Setting those two equal to each other, we end up with mass of our system times the acceleration is equal to the tension force minus the friction force. And now I'm ready to do some thinking about the particular problem. I'm looking for the tension force, and so I'm going to isolate this value right here, that tension force. But to do that, I'm going to add the friction force to the other side of the equation, and I end up with the tension force on block 1 by the rope is equal to mass times acceleration plus the friction force because it was added to the other side of the equal sign. And then I've highlighted there that I've replaced m with m1, the specific mass value for the system we are analyzing. And now I look at this, and on the left side of the equal sign is my find. Everything on the right side of the equal sign is in my givens list, and so we can plug in numbers. The tension force on block 1 by the rope is 5 kilograms times 1.80 meters per second squared plus 15 newtons. Another way to think about that is the tension force has to be bigger than the friction force of 15 newtons by an amount equal to ma. And when we evaluate that, we find that the magnitude of the tension force on block 1 by the rope is 24.0 newtons. And since part B just asks for the magnitude, how strong the force is, we can stop there. We don't need to indicate direction for our final answer. We are now ready to look at part C of this problem. Part C asks us to determine the amount of time it takes for the hanging block to fall 1.25 meters, assuming it starts from rest. I know things about distance and speed. I'm looking for a time. So now I'm thinking it's going to be one of those motion equations that's going to be helpful here. And I'm analyzing the hanging block falling. So the system I'm going to look at for part C of this problem is the hanging block. I'm going to write my new givens list for part C. It's everything we had before, plus a few more things. We now know the tension force is 24.0 newtons from part B of this problem. But part C gave us some new givens. We know it falls 1.25 meters, so I'm going to choose to make my starting position 0 meters, and in doing so, I know my final position is 1.25 meters. The starting position is an arbitrary choice that you get to make, and so I often like to make it 0 meters. We also know it starts from rest, so even though the number 0 isn't explicitly written in part C, we do know that the initial velocity is 0 meters per second. And so I go look at a list of all of the different motion equations we have from our study of motion earlier this year. And you might find, oh, hold on, no, we're looking for time, sorry. So you do that, you go look for an equation where t is the only variable that's unknown in that equation. And you've got this stuff over here that is known. And if you do that, you may find this equation where t is the variable we don't know. But if we go left to right, I know my final position is 1.25 meters. I know my initial position is 0 meters. I know my initial velocity is 0 meters per second. And I know my acceleration is 1.80 meters per second squared. And so t is the only thing I don't know. Now, typically, for my class at least, I say you can't plug in numbers until you've isolated the variable you're trying to find. There is one exception to this rule, and the exception is you are allowed to plug in zeros early because it will make your algebra easier. And so I'm going to go ahead and plug in the zeros right now. We have the initial position was 0 and the initial velocity was 0. And in doing so, 0 times t, this whole term is 0, plus another 0 term. The only thing that will be left is the 1/2 at squared in the end. So we can write that as is. Notice I didn't plug in the final position and I didn't plug in the acceleration yet because the find is not by itself, and those are givens that are not 0. So I can't plug those in yet. But plugging in the zeros did make my life easier. Let's go ahead now and do a little bit more algebra. I can multiply, I'm ready to now isolate t. To do that, I'm going to start by getting rid of the fraction 1/2. I don't like working with fractions. To do that, I can double both sides of the equation. Multiplying through by 2, the left side of the equal sign becomes 2 times the final position, and the right side of the equal sign becomes acceleration times time squared. 1/2 times 2 multiplies to 1. I can then divide by the acceleration, and I have an expression for time squared. And then I want time, so the last step here is to take the square root of both sides. And when I do that, I end up with time isolated by itself on one side of the equal sign, and the other side of the equal sign has things that are in my givens list, the final position and the acceleration. I'm ready to plug in numbers now. So the time is the square root of 2 times 1.25 meters divided by 1.80 meters per second squared. And when I evaluate that, I end up with this time value of 1.18 seconds. I put a box around that, and I have completed the problem. So we have found the system's acceleration by looking at the 2-block system. We have determined the tension of the rope by looking at the system that just consists of the block on the table. And we've used some kinematics, some motion equations, to find the amount of time it takes to fall 1.25 meters by looking at the system consisting of the falling block. Thank you for watching, thank you for learning with me, and I hope you have a great day.